Hello everyone, and I welcome you in this lecture on performance measures. Before we discuss more sophisticated supervised learning algorithms, it is important to consider different performance measures because each of them give us a different insight about the performance of the algorithm that we have applied. So far, we have discussed these three supervised learning algorithms. One is linear regression, KNN, K nearest neighbor algorithm, and decision tree. Just remember that the first one is used for regression problems, and the last two we saw them in the context of classification problems. Related to linear regression, we saw one performance measure called mean squared error, and in the classification case, we saw only one performance measure called classification accuracy. However, there are other performance measures as well, which give us a different insight about the performance of the algorithm. Today, we will look into that. So, the content of today's slides are as follows. First, we will discuss different types of performance measures. There are error measures also for regression problems. We will look into a very specific kind of matrix called confusion matrix, and we will discuss some other measures also like precision, recall, AUC score, and others. So let's first discuss the performance measures that we have already seen. As you know, that performance measures help us assess how good the algorithm is working. So far, we got familiar with the following two matrices. Mean squared error, MSE, is used for regression tasks. It is a measure of average squared differences between the estimated value, so y cap here represents the estimated value, and the actual value, which is y. A lower error indicates that there is less difference between the actual and estimated values, and it also means that the model predicts more accurately. On the other hand, for k nearest neighbor and decision tree algorithms, we discuss classification accuracy. It is a matrix for evaluating classification models calculated as the ratio of correct predictions to the total number of predictions. It measures how often the model predicts the correct label for the input data. High accuracy indicates that the model performs well in identifying the class labels, but it may not always reflect the model's effectiveness, as we will discuss in this lecture. So, MSE is better when it is lower. However, classification accuracy is better when it is higher. Let's see one example to calculate mean squared error. Let's say I have given the x and y pair and I tried to fit a regression line. Let's say that using linear regression, I got this line where the estimated value y dash, sometimes we use y dash, sometimes we also use y cap here, is 9.2 plus 0.8 times the x value. So using this regression line, we can calculate the estimated value of y dash like this. So how can we calculate the mean squared error? For that, we will first calculate what is the difference between these two terms, y the actual value minus y dash the predicted value. Once we have calculated that, then we calculate their squared values. Okay, so this is just the square value of the difference between the actual and estimated values. We got these values for 5 records, 5 examples and observations. Finally, MSE can be calculated as the sum of the squared terms divided by the total number of examples, which is 5. So, for this specific case, our MSE would be 6.08. Let's discuss how we can calculate the classification accuracy also. Let's say I have been given this classification data set where I have 3 independent variables and 1 dependent variable, which is y. Now let's say using some classification algorithm like k nearest neighbor or decision tree, we calculated the estimated value of y, which is y cap, right? So sometimes the predicted value agrees with the actual value. So the actual value was yes, and the predicted value is also yes. Sometimes there will be a disagreement where the actual value was no, but the predicted value is yes. So when we see this whole prediction and actual values, we will see that out of 8 total number of examples here, in 6 cases, the algorithm predicts correctly. However, in 2 cases, it predicted wrongly. So the classification accuracy is correctly classified instances 6 divided by the total number of examples 8, and sometimes we also multiply that with 100. So in terms of percentage, it would give us the classification accuracy 75%. For regression, there are other measures also, I should say error measures, which are similar to mean squared error, but they give us different values. So this is our MSE, mean squared error, that we have already discussed. There is also mean absolute error called MAE, where rather than calculating the squared of the difference like in MSE, here we calculate the absolute value of the difference between the actual value y and the predicted value y cap. We also have a measure called root mean squared error, RMSE, which is the square root of MSE. So we can also write it like this. Often in the case of mean squared error, since it calculates the square of the differences, if the difference between the actual and the predicted value is large, then overall this squared term becomes really huge. In order to compensate that, root mean squared error, calculate the square root of MSE. There is also very famous performance measure in the case of regression problems. It is called R squared or coefficient of determination and calculated like this. Here y represents the actual values, y cap represents the estimated values, and y bar represents the mean of the actual values. So R squared, also known as the coefficient of determination, is a statistical measure that represents the proportion of variance in the dependent variable which can be predicted from the independent variables. This R square is used to know how well our data captures the underlying pattern in the data. Also, it serves as an indication of goodness of fit of our model. Usually, a high R squared value suggests that our model has a strong correlation with the actual outcomes, thus providing a reliable basis for predictions. Its values range between 0 to 1. A value closer to 1 indicates a model that accurately predicts the dependent variable, while a value closer to 0 suggests that the model fails to accurately capture the underlying trend. A high value of R square indicates a good fit between the predicted values and the actual values. It signifies that a significant portion of the variance in the observed data can be explained by our regression model, highlighting its effectiveness in making the predictions. There is also an upgraded version of R squared called adjusted R squared value. Adjusted R squared also considers the number of independent variables in the data. This consideration was absent in the normal R squared calculations. So sometimes you will find R squared values, and sometimes you will also find researchers calculating adjusted R squared value, because it is considered better than the normal R squared values. Then for classification measures, we have other measures also than classification accuracy. The commonly used other representations are confusion matrix, and these two matrices, precision and recall, they are also used very commonly. Let's see what are they. Let's first start with the confusion matrix. Confusion matrix is a table which describes the performance of the classification model. It allows the visualization of the performance of an algorithm. Here you see this is a confusion matrix. In this matrix, we put actual values on one side and predicted values on another side. Let's say there are only two classes, positive classes in the data and negative classes in the data. There are actual positive values here and actual negative values here. So when we put them in this way, there are four possibilities that emerge. Either we fall into the cell TP, TP stands for true positive. True positive represents that the actual values were positive and the predicted values were also positive. That's why they fall in this cell where actuals are positive and predicted values are also positive. Then we have this cell, it is called Tn. Tn stands for true negative. True negative means that the actual value was negative, that's why we are here, and the predicted values are also negative, that's why we have Tn in this specific cell. These Tp and Tn values, if they are bigger, it means the performance of the model is good. However, we also have Fn and Fp value. Let's start with Fp. Fp stands for false positive. False positive means that actually the value was negative, but our algorithm predicted this as positive. So you can consider an instance where the actual value was no, but the predicted value turned out to be yes. You can remember Fp or false positive as falsely predicted positive, which means that the actual value was no, but it is falsely predicted as positive. Similarly, we have the concept of Fn, which means false negative. As you can expect, false negative here means that the actual value was positive, but somehow our algorithm predicted negative. So the actual value maybe was yes, but our algorithm predicted as no. You can remember Fn or false negative as falsely predicted negative. What does that mean is it was actually positive, but it is falsely predicted as negative. So Fp and Fn are the problematic values. If they are less in our confusion matrix, it means our algorithm is doing good. Let's try to explore further how we can calculate all of these four values, Tp, Fp, Tn and Fn. Let's say this is our data set, which we have seen earlier also. This is the actual y value and this is the predicted y values. So out of total of 8 examples, so there are total 8 examples here. In 3 cases, the actual value was yes and the algorithm also predicted yes. So this is the case, this is the second case and this is the third such case. So there are 3 instances of true positive. Once again, true positive means that the actual value was positive and the algorithm also predicted positive. On the other hand, we have 3 true negatives also, where the actual value was negative and the algorithm also predicted negative. So they are true negative values. On the other hand, we have one instance, this specific instance, where the actual value was no, but the algorithm falsely predicted positive. So this is an instance of FP, falsely predicted positive. It was actually negative. And we have one instance of Fn also, false negative, where the actual value was yes, but the algorithm falsely predicted it as negative. So we have one value here as false negative. So this is how we calculate our confusion matrix. Remember, when we do not have confusion matrix, when we have only accuracy, in that case we do not have a good understanding of FP values and Fn values, because accuracy focuses only on true positive values and true negative values. But depending upon the application, in some specific cases, our focus shifts toward false positive values and false negative values. We will see some of those examples. So the confusion matrix, about confusion matrix is large values of TP and Tn, they are good, and large values of Fn and Fp, they are problematic and we should avoid them. If you go by this whole column, it gives you the total predicted positive. These are rightly predicted, true positive, and they are falsely predicted, but overall we got these many total positive predictions. This column gives us total negative predictions. So we have rightly predicted negative and they are wrong, but the total predicted, you can calculate it like this. So in both the cases, total predicted positive are 4 and total predicted negative are also 4, adding both the cells. Similarly, this row here actually tells us total actual positive, and this row here tells us total actual negative. Now let's see the precision measure. The precision for a confusion matrix is calculated like this: TP divided by TP plus FP. And as you can imagine, if you have low values of FP, then you will have a higher value of precision. Precision can also be written as TP divided by total predicted positive, because TP and FP, if you add both of them together, they give you total predicted positive values. So this is how we calculate our precision. Similarly, we also have the recall value. The formula of recall is given like this. Recall value will be high when false negative are less. So if you have low value of Fn, then you will have a higher value for recall. The formula of recall can also be written like this. It is called TP divided by total actual positive, because if you add TP and Fn, they will give you total positive values. So about precision and recall, they are preferred over accuracy in situations where there is a significant imbalance between the classes of interest, or when the cost of false positives and false negatives, they vary greatly. Specifically, they are critical in fields like medical diagnosis, fraud detection, and information retrieval, where identifying the relevant cases, means true positive, accurately is more important than the overall percentage of correct predictions. Precision is crucial when the consequence of false positives are high, whereas recall becomes essential in scenarios where missing out on true positive carries a greater risk or cost. Precision measures the accuracy of positive predictions made by our model. Specifically, it calculates the proportion of predicted positives that were corrected identified. However, high precision indicates that the model is effective at minimizing false positives. Recall, on the other hand, measures the model's ability to identify all relevant instances. It calculates the portion of actual positives that were correctly identified by the model. So, high recall value indicates that the model is effective at capturing most of the positive cases. It is also important to note that precision and recall often have an inverse relationship. That is, enhancing one typically comes at the expense of the other. So, balancing these matrices is crucial for developing a model that is both accurate and comprehensive. Let's try to understand the situation where we can use precision as a performance matrix. Let's consider this case, where on the basis of some independent variables x1, x2 and x3, we want to predict whether the person or patient has cancer or no. So, we have the no answers and we have the yes answers. In this specific case, precision should be a preferred matrix. Why this is the case? Because precision includes false positive and we want to avoid false positives in this case. False positive here refers to that no case or non-cancerous case should be predicted as a cancerous case. We want to avoid this situation, and precision will give us a better understanding of how many false positives or such cases are there. If precision value is higher, closer to 1, which means there are less cases like this, and this is what exactly we want for this specific application. We do not want to predict non-cancerous patients as the cancerous patients. On the other hand, let's consider another scenario where we have some independent variable, some weather related variables, and we want to predict whether tsunami might hit or no. Alright. So, in this specific case, recall should be the preferred value. Why? Because we want to avoid false negative cases. False negative here represents that we want to avoid cases where yes is predicted as no. So, a tsunami means yes case should not be predicted as normal weather, which means no. So, if the recall value is high, it means we have less cases like this, which ultimately represents that our model will not predict tsunami case as the normal case, and this is what we want. So, precision and recall, they are used depending upon the application. In some cases, we want to avoid false positive cases. In those situations, we should go for the precision value, and in some cases, we want to avoid false negative cases. In those cases, we should use recall metric. There are other performance measures also. Most famous of them are sensitivity, specificity. AUC score is very commonly used metric, and then we also have the F1 score, which is the combination of precision and recall. So, these matrices are also used very commonly. By the way, sensitivity is the other name of recall metric. Out of them, area under curve score is used quite commonly. It is based on a curve called receiver operating characteristic curve. So AUC stands for area under curve. It is a performance metric to evaluate the ability of a classification model to distinguish between classes. It captures the performance of a classification model at all classification thresholds. We will discuss classification thresholds later on in this course. It shows the trade-off between the true positive rate and false positive rate. So false positive rate is calculated like this. True positive rate is calculated like this, and false positive case is calculated like this. Then we plot them, and plotting them give us the ROC curve. And the area under this curve is called the AUC score. The value of AUC varies between 0 to 1, and AUC score of 1 indicates a perfect model that captures the positive and negative classes for all possible classification thresholds. And a score of 0.5 suggests that a model does not do better than the random guesses between the two classes. And a score less than 0.5 implies that the model performs worse than even the random guessing, which usually indicates that there is a problem with the model. So an AUC score between 0.5 and 1 indicates varying level of model performance, with a score closer to 1 signifying better model discrimination abilities. So this is how AUC is calculated. We plot false positive rate against true positive rate at different thresholds. So this point here represents a different threshold, it represents a different threshold like this. So this curve is called ROC curve. This is the 0.5 value, which represents the random guess, and the whole area under the ROC curve is called the AUC score. So as conclusion, we discussed various performance measures. Each of them give us different insights about the predictions. These measures can easily be calculated using the standard machine learning libraries that we will see during the implementation of different algorithms. Thank you.